Thank you. And today I have kind of great pleasure in introducing, welcoming our colleague, a long-standing collaborator of mine, Dr. Samuel Godfrey, who is an honorary professor in the Bartlett School of Sustainable Construction. His day job is at UNICEF, where he is the regional WASH advisor for East and Southern African region. And he provides kind of leadership and insight into kind of areas of climate change, infrastructure delivery, sustainability in complex settings. His role with us is a UN-approved collaboration partnership. And the purpose of this collaboration and partnership is for us to join forces to provide thought leadership on the challenges facing us in the future, and particularly in Africa, around the need to provide infrastructure in very complex and challenging settings. What are the levers and drivers for those? And also thinking about how to do it in a way which is climate resilient, which is sustainable, which requires engagement with local communities and stakeholders. And I mean, Dr. Samuel Godfrey has had over 25 years experience on the ground on infrastructure delivery, on stakeholder engagement. So he has a lot that he can bring to the conversation today. And I'm so grateful, delighted that you are able to join us today and spend time in this conversation with us. So over to you. Thank you so much.
Great. Thank you very much, Priti, and good morning, good afternoon to everybody. Over the last 25 years, I've been driven to find solutions to deliver water infrastructure in complex environments. And I've learned, I guess, from experience of working in IDP camps in Angola, delivering urban water infrastructure in Mozambique, and more recently deploying remote construction monitoring technologies like biosensors in Somalia. And my interests really, as was mentioned by Professor Priti, really lie in this interface between my industry, so the water industry, and its need for increased water asset delivery and really research and innovation. So maybe before I start, let me thank really many of the collaborators over the years that have worked with me, some of them on the call today, plus of course family and friends who have been really very supportive in sort of delivering on this mission, on this dream to date of improved water service delivery in complex environments. So just allow me then to start with sort of taking us back to 1998, 25 years ago, where I was introduced to Steffi. And yeah, Steffi is not a person. Steffi is not a robot. In fact, to the contrary, Steffi is a multidimensional approach to infrastructure delivery. And Steffi really stands for all of the sort of values of delivering water assets in Africa. It relates to the S, which of course is the science behind water service delivery, the T, which is really the technology, the E, which is the environmental components, the F, which is the financial, the I, which is the institutional arrangements, the regulatory environments in which assets are delivered, and finally E, which is the economics, making systems work economically, both for consumers, but also for utilities. So sort of having Steffi in the back of our minds, today during this talk, I wanted to really focus on three components. Firstly, to really try and set the scene a little bit on what are those complexities that we're dealing with in delivering climate resilient water systems in Africa. Secondly, to talk through the Sustainable Development Goals and some of the recent research and work that we have been doing in collaboration with the Bartlett School on the implications of the service norms of the Sustainable Development Goals. And finally, some climate resilient water solutions. And the main bulk of my talk will be focused on climate resilient water solutions, which I really hope it will sort of generate some thoughts and stimulate some ideas that you might want to put in the Q&A for our discussion towards the end of this talk. So sort of just turning to, the first key sort of big ticket issues. So Africa, as we know, has about 10% of the world's water resources, but it has about 20% of the world's population. And if we're putting these two things together and looking at demographics, which I'll go into some level of detail on, we can see that very soon the demand is going to outstrip the supply. And this is, of course, a major challenge for all of us that are involved in water asset and water supply delivery. And particularly in areas which are affected by the increasing changes in the meteorological cycle, the increased levels of flooding and the increased levels of drought. Equally, we know that in Africa, of course, we have a very low population density in many areas of less than 50 people per square kilometer, which of course, in comparison to many Western or developed countries, is very low and adds an additional layer of complexity. So population, of course, is a driver for any asset design. When we're looking at the design of a water supply system, we look at the design horizon, usually over a 20-year period, and we look at how many people it will serve in 20 or 30 years. And of course, in Africa, one of the challenges we've always had is that the exponential growth of the population is meaning that many of the water supplies that I was even involved in back in the 1990s, early 2000s, are no longer supplying the number of people that we thought they would supply in 2020 due to the complete change in the demographics of the continent. This slide, of course, shows the population by region in billions. And what you can see from the slide is that if we look at the Asian population by 2050 compared to Africa, there's still a massive difference in the number of people in Africa compared to Asia. But by 2100, we're expecting almost 4.3 billion people to be living in Africa, which of course is only 80 years from now. So if you're designing a water supply system in the next 10 years for the next 10 or 20 or 30 years, you're going to be seeing a massive change in the number of users that we're going to have in that particular catchment. Additionally, if we look at the area of Eastern Southern Africa, which is the area that I'm currently responsible for, I'm based in Nairobi, and I look specifically at the delivery of water supplies for the population of Eastern Southern Africa. We can see here that the demographic dividend between the population under 18 and that over 18 is going to see a massive shift. If you look at 2018, we had about 251 million people that were between the age of 0 and 17. And by 2100, that's going to almost double to 468. Now, where those people then are living is of great interest to us. This is a graphic from UNDESA, which we use very frequently to try to design our water supply systems. And it lists, of course, on the left, all of the names of the countries in Eastern Southern Africa, and it shows where they live now and where they'll live in 2050. And the green are the rural communities, and the blue are the urban communities. And you can see really clearly, just taking the examples of the top two, Ethiopia and Tanzania, that we're seeing a massive, massive level of urbanization that is going to occur and is occurring between now and 2050. So how do you design, how do you plan for these populations for water supply? Bearing in mind, of course, that many of these populations are populations that are living in coastal areas. This is a piece of research that I did with UN Habitat and UNICEF back in 2019, where we looked at trying to estimate the population density of all the urban areas across sub-Saharan Africa. We released this report at the World Urban Forum in Qatar in early 2020. And you can see here that it's very, very clear that the coastal areas of the continent are the areas where we're having the largest populations. In West Africa, you can see by 2030, a lot of orange dots, which means cities which are greater than a population of 5 million people. And similarly, if you look into East Africa, you can begin to see the same across the coasts of Kenya, Tanzania, through Mozambique. And so what this is really essentially telling us is that the populations that we need to design for are not only growing and not only urbanizing, but they're also very clearly located in a lot of the coastal areas. Another interesting component of the demographics, though, is also some work that we did with UN Habitat, which we published in 2019, which shows that the rural to urban migration of Africa is different from the rural to urban migration of South America or Asia. We know, for example, that between 1970s, 1980s up till today, much of South Asia has urbanized, but in South Asia, it's been rural migration to large megacities, whether it's Mumbai or Delhi or Dhaka. We've seen a huge shift from rural communities to urban areas. And the same thing happened in Brazil, and the same thing happened across Latin America. But in Africa, what's happening is a really interesting phenomena, is that much of the migration that's occurring is actually not occurring between rural areas and megacities. It's actually occurring between rural areas and these small secondary cities. In fact, 46% of the urban population in Africa now lives in cities below 300,000 people in population. Now, if we look at the growth of the population, of course, that is going to grow into larger cities. But these secondary cities at the moment are really the growth points for where we can develop climate resilient water systems. And much of the planning that's going on in Africa at the moment is around improving climate resilience of water systems for these secondary towns. The graph on the bottom compares sub-Saharan Africa, which is the blue line, with other low-income countries, which are the red lines, and then the rest of the world. And you can see that where populations are 1 million or more, they're obviously much, much higher in other low-income countries and the rest of the world in comparison to sub-Saharan Africa. So this is really a key focus for the design of assets. When we're looking at prioritization of areas for infrastructure, it's important for us, first of all, not only to understand the potential demand curve for the design life of the system, but also geographically where we can focus based on this level of information. Now, another interesting layer of this, of course, as was mentioned by Professor Pretty at the beginning, is the impacts of climate change on these particular urban settlements. This is a graphic from a piece of research that we've done with Professor Pretty, which we're currently publishing in Nature. And you can see very, very clearly that the sparsely populated areas compared to the densely populated areas are unfortunately many of them overlaid with some of the key hotspot risks of the continent. So we have, of course, in Africa, the risk of the high levels of precipitation. We have the risks of lower levels of precipitation. We've got the issues around coral bleaching, which, of course, is a major challenge for the fisheries industry and is leading in many ways to a change in the levels of livelihoods in rural areas. We're also seeing, of course, sea level rises, and those sea level rises are indicated on this graphic, are of course leading to saline ingress of much of the groundwater in those coastal areas, which of course affects not only the salinity of the soil and the fertility of the soil for growing crop, but also of course leads to populations moving further away from those main coastal areas in search of cleaner aquifers and cleaner water supply. And of course, we've got also the whole issues which are related to the changes in the overall ecosystems, which when we take the main basins that we have, the Zambezi Basin, the Lake Victoria Basin, or the Chad Basin, all of these within Africa are the basins which are feeding the water systems, which ultimately are going to lead us to be able to identify the more climate resilient solutions for those areas. So this piece of work, piece of research, of course, then links very, very nicely to the 6th assessment report of the IPCC. Of course, the IPCC's 6th assessment report will be released and discussed in much more detail at COP27 in Egypt next month. And this particular piece of research that we've done has been really instrumental in informing a number of the other UN agencies of what are the specific challenges to the water systems in Africa that we need to consider in terms of water supply. So what I've tried to do in this first section of the presentation is talk a little bit about the background. So we've talked a bit about the demographics, the importance of the increased number of people that need to be served, of course, by water, where people will live in terms of the move to smaller cities rather than mega cities, and also the challenges we're facing in coastal areas, particularly where we have large urban settlements and where we're seeing major impacts of climate change. So now let me move on to the second part, which is really around the Sustainable Development Goals. And of course, the SDGs, which are our targets globally up to 2030, estimate through the UN High-Level Panel on Water that we need approximately $114 billion per year in CapEx and about $129 billion in OpEx globally to be able to achieve SDG 6 for clean water and sanitation, particularly 6.1 and 6.2. And of that, 36 billion in CapEx, so just under a third of the global demand is for Africa. So if there's a real need to talk about major infrastructure development, looking at mega projects, looking at mega solutions, clearly it's going to be important for us to invest our time and our effort to be thinking a little bit more around the actual fund or available finance that will need to be available for CapEx in Africa. The other thing to say is that in SDG 6, there is a higher service level required. Those who are on this conversation today will be aware that there's a different level of service required under SDG 6.1 and 6.2 compared to the previous Millennium Development Goals. And we will need, of course, around 15% more of investment. At the moment, the investment costs that we have for Africa are at around 3% of the total target. Just to reach the very basic level of infrastructure, we will need an additional 15% per annum. So what we've done in this particular piece of research, and I've listed it at the bottom there, it's a recent piece of research that we've done again with Professor Pretty in UCL, is we've actually validated a fiscal diagnostic tool which helps you understand where to prioritize infrastructure investments using the analytic hierarchy process, the AHP. And of course, the AHP, which was developed by Sati in Sudan back in 1980, is an extremely important multi-criterion analysis tool for infrastructure planning. And what we have done is we've applied the AHP in this piece of research to the SDGs in Africa to really help us identify what would be the most appropriate areas for investment, but also what would be the best technologies for investment in those areas. And of course, when it comes to infrastructure planning, the AHP has applications in many ways, but we found it to be extremely effective in also helping us understand what sort of cross-border technologies or what sort of cross-border approaches we could adopt through what we call the portfolio approach to financing, whereby we're taking a specific type of technology or approach with a utility and applying it across a number of countries to de-risk one country against another. Now, the reason for that, of course, is if you look at this piece of research, you'll see is that in many African countries, we've seen quite a shift politically over the last 10 or 20 years, some towards demographic stability, some in and out of demographic stability. And of course, it means that if we are planning infrastructure in one country that is deemed to be perhaps high risk from an investment perspective, we need to de-risk that as much as we can with a stable country so that we're able to offset those particular challenges which are associated with one member state to another. And so what we've done in this paper is we've looked at those portfolio approaches to try to then demonstrate how the AHP can be a useful analytic tool to be able to achieve that goal. So what are those particular types of technologies? And this is now where we go back to Steffi and we think about, approaches, on the engineering side of what could be good solutions for these types to address these types of challenges that I've outlined at the beginning of this talk. Well, in the MDGs, of course, we were all focused globally on MDG 7 and ensuring the environmental sustainability. And as you recall, the MDG 7 had a target of halving the number of unserved population by 2015. So if there was already a very low baseline, the halving of that, of course, was relatively easy in comparison to SDG 6, which is saying that we want universal access to water by 2030. Now, the universal access, which of course we started from 2015, and we're now 7 years into this particular SDG, it moved very much the technology selection from what was essentially a kind of low-cost self-supply technology, where we were looking at the development of wells and springs and shallow groundwater systems, towards slightly more complex systems where we're looking at pipe water reticulation, where we're looking at water resources and supply network systems which interconnect urban and rural areas, but also that address the issues of the water resource, the catchment, and begin to quantify from a water management perspective what water is available for those populations. So where we are at the moment is we're very much on the right side of this slide. So we're at the stage where we need to be investing and developing we would call larger scale projects, which will enable us to meet the demands of a larger number of populations. So if we look at that, what are those types of technologies then that we would like to focus on from a climate resilience perspective? And it's always good, I think, to look back, right? It's always good to look back at what we've done and learn a little bit from those experiences. And the publication which is here on the slide is a publication that we published in 2020 in Nature Communications, which is of course part of the group of Nature journals. And I published this with the British Geological Survey, and it was based on an analysis of our response to the 2015 and 2016 Horn of Africa drought in Ethiopia. And what's very interesting in the slide is that we looked at the temporal data sets from around 5,196 water supplies across the country. And you can see the maps. There are maps of Ethiopia. You've got the altitude zones on the top. You've got the hydrogeology, and all of those yellow dots, which are there, are all the water supply systems that were included in this temporal data set. And then we analyzed those against the different geologies. So looking at the different sediments, looking at the permeable lenses, looking at all the different groundwater flows between the highlands and the lowlands of Ethiopia. And we assessed whether or not one technology versus another was resilient to climate shocks, in this case to droughts. And the results of the research basically showed that after millions and millions of dollars of investment, which went in both to the infrastructure that we put into Ethiopia, but also to the emergency response that went on in 2015 and 2016, we concluded that the boreholes that were accessing the deeper groundwater actually performed better during the drought than any other technology. And if we think about it from a perspective of recharge, looking at saturation of the surface water to groundwater interaction, it becomes clear that when we have rainfall, which comes into the higher altitude zones of a country, there's clearly going to be some level of interconnectivity between that rainfall and a time lag between the interconnectivity of that rainfall and the recharge of the groundwater in other areas. And we found that with good siting of these deeper boreholes, we were able to supply water to communities, to towns and to villages throughout the drought in a climate resilient way, in a sustainable way. So this is a very important learning, because unfortunately we are currently also in a similar level of drought, or if you like, change in meteorological cycle in the Horn of Africa now in 2022. And again, I need to keep reiterating to colleagues that are involved in this, that if we plan for assets in 2022 now, we need to invest in these deeper groundwater assets to ensure not only the resilience of the users today, but also perhaps for the users of the next change in meteorological cycle, which unfortunately is probably, with climate change, going to happen in the next 2, 3 or 4 years of time. So how do we do this essentially? What are the kind of secrets behind the areas of work that we looked at from a climate resilient water system perspective? We developed, and we published in this article, which is there at the bottom of the slide in 2016, we published a paper on the three-phased methodology to groundwater investigation and development in the Horn of Africa. And the methodology essentially optimizes the use of low-lying satellites, which of course have increased exponentially across Africa with the advent of the mobile phone technology. And we use those low-lying satellites to undertake remote sensing of areas which were previously not mapped and previously not known, and looking at the different aspects of them, whether it's the sort of geomorphology or the drainage or the slope or the structure, even the structural density of those areas. We were really able to capture, using the remote sensing, very detailed information on those particular zones of Ethiopia. And we then used that with the hydrogeological information and geophysical information to undertake step 2, which was the ground truthing. And again, we used within this ground truthing a multi-criterion analysis, which was based again on the analytic hierarchy process. We validated it as well with physiological statistical analysis. And we were able, on the basis of this, to identify what you can see in the map there, areas which were areas of high suitability, which are in green, for groundwater development. So these are areas essentially which are in a desert where if you stood and you looked out in the desert, you would only see sand, and you wouldn't be able to say whether or not under that sand there would be any groundwater at all. And using this technology, we were able to identify specific saturation zones where there was a high, medium, or low probability of accessing the groundwater. We then combined that, of course, as you can see in the bottom, with the 3D resistivity maps. And we use those for the logging to be able to say which are going to be the blue areas. The graphic on the bottom is essentially showing the saturation zones where we have high potential for the saturated zones for the groundwater. And so using that, the map, or the last component, which is on the left, combines it then with the actual topography, the slope in the areas. And you can see then that there will be different depths that will be needed based on the drainage patterns between the surface water and the groundwater in those areas. Now, this technology has been revolutionary in identifying areas where we can access water in a sustainable and climate resilient way during, before, or after droughts. And of course, it's meant that there's now an increased level of interest and investment in this particular technology. But some of the colleagues worked then with me, and particularly colleagues from Ethiopia, some of the experts there, on sort of seeing, well, is that water that we've identified actual fossil water, or is it really climate resilient? Meaning, is it water that's been there for millions of years, and because we're changing the atmospheric patterns in the planet, we're getting less rainfall, and therefore we're having to drill deeper and deeper into water that in fact has been there for millions of years? Or is this water that is interconnected with rainfall? So when the rainfall fell 10, 20, 30, 50 years ago, did it recharge that groundwater? And the only way you can find that out really is to undertake isotope analysis. And so we did that, and we used this graphic that you can see here, where we've got on the left there, the recharge, which is looking at, more than 1,000 millimeters per year, or looking at 100 to less than 50, or less than 50 millimeters per year. And then we have the effective storage capacity, which is, of course, the specific yield versus the aquifer area versus the saturated thickness. And we tried to estimate this for areas which had decades, years, months, or days, to see what would be the impact. So if we had a heavy rainfall, let's say last month, what would be the impact of that on these deep aquifers? Or if we had a heavy rainfall 50 years ago, what would be the impact on that? And of course, we age the water using the isotopes, which enables us to make the association as we take the water samples out of the wells with that specific interrelation between the two. And this is fundamental research which can inform climate resilience, because without understanding the relationship between the rainfall and the groundwater, it's obviously very difficult for us to be able to say with confidence that the technology of identifying the groundwater is actually going to be sustainable in the future. And then what we tried to do was we developed a tool which will overlay both the groundwater investigation, the isotope analysis, with the selection of technology, so that we would be able to inform contractors on what sorts of tenders, what sorts of design we need for those particular areas. So that could be to design for deeper wells, it could be a combination of more shallow and deeper aquifers, it could be looking at a combination even of springs and wells, and having an understanding then on the basis of that of which particular areas of the country are more appropriate for those types of technology. So this is really an infrastructure planning tool which is climate resilient, because again, it's giving you the ability to be able to inform as a leader where particular assets should be prioritized, how they should be costed, what sort of level of capex is going to be required for that area to be able to deliver a sustainable, financially sustainable, but also from the perspective of STEFI, an environmental and economic sustainability for those types of technologies. Now, once the actual source, of course, has been identified, what we have then focused on mostly is a solution which, of course, is now happening a lot in China, in East Asia as well, of water transmission schemes. So transversal schemes to take water from one area of the country where there is enough water, but not many people, towards another area of the country where there are a lot of people, but there's not a lot of water. And this is really the crux of the solution, because clearly we can't do that if we don't do all that detailed scientific investigation that I've just explained on the previous slides. But once we've done that, we then need to be focusing on much larger water transmission schemes, which will enable us to balance population with demand. And if we again go back to what I was saying at the beginning of, large coastal populations which are growing, the freshwater sources for those populations is clearly not going to be coming from areas that are close to the coastal areas. It's going to be coming from inland. And if it comes from inland, it's going to be coming more inland than we currently have been doing before because of the saline ingress. So this is an example of a scheme, just as an illustrative example. We've been involved in hundreds of these types of schemes. But this is just one example, just to sort of make the point on the transversal schemes between one area to another. So the demand of the town, which is on the right-hand side of the map, is about 1,700 megaliters per year. So it's just less than 5 megaliters per day. And you can see that it's not just the town, but it's also interconnecting the surrounding rural communities to make sure, again, that the SDG targets of universal access are met. So it's not transversing through communities, it's connecting communities, which of course enables us to have an economy of scale and be able to produce the amount of water that we need from one area to another. The borehole yields using that methodology that I explained before are extremely high, 83 liters per second, which of course means that we don't have to have constant pumping, which of course is good from a carbon offset perspective because we can pump intermittently. We can also look at renewable power to enable us to increase our storage and reduce our pumping. We looked at having very large service reservoirs for the scheme, which are service reservoirs across the network to balance the storage requirements with the demand requirements and use as much as possible gravity as the main energy source for the schemes. The transversal schemes in this case are looking at about 180 kilometers of pipeline. And so when you start to pump water from one area to another, of course, without using all of these different aspects of balance, of power, of gravity, we will get into a situation where the actual cost for the consumer at the end becomes very expensive because of the pumping costs. And so we took into consideration in all of these schemes the climate resilience of every component of the infrastructure, from the source, as I mentioned, to the energy, which is going to be required for lifting the water, to the storage, to the gravity, and of course, even the pipe material, the pipe diameter that you might need for the transmission mains. Of course, we want to reduce the roughness factors of the pipes so that we're able to get higher flow through the system, which of course then reduces the friction, which will enable us to be able to supply water at a much higher rate, at a much quicker rate, and at a cheaper rate for the consumer. And this particular system then links with 37 kilometers of secondary and tertiary distribution, which of course then interconnects all of these different areas. Now, this kind of investment is what we would consider to be a climate resilient investment, because and ultimately it's not going to lead to overexploitation of the aquifer due to the balancing, the isotope work, looking at the competing demands on the aquifer from agriculture, from industry, but also it enables us to have a system which can be managed by a professional service. If we look at the data from the UN, particularly in Africa, it's showing that for rural water systems, many of them, I think it's up 70% of them, are non-functional after 5 years of construction. And the main reason for that, of course, is to do with the OPEX model and the way that the OPEX model has been based in historically on a community-based management system or a voluntary-based system. So by moving into these kind of pipe network systems, which enable us to have transversal schemes of moving water, let's say, from a very dry area of Somalia to an area where the population happens to be settled for security reasons, or an area which is from a highland where we have plenty of water, but where people are not currently living because they're pastoralists and they're living more in lower areas, we're able to move the water from one space to the other, but then we need to put in place some sort of delegated contract for a private operator to be able to ensure that the tariff that's charged will bring some level of return on investment, but also it will lead to the covering of the OPEX costs for that particular supply. And of course, it's not in these cases, it's not going to open the door to all forms of concessional finance. It will open the door to particularly blended finance, because it will enable us to place grant funding to be able to construct, or public resource funding to be able to construct the CapEx. But then we can blend that also with private sector. It could be a PPP, or it could also be through concessional loans, which can be offset against the grant, so that the payback period for those loans through the commercial utilities is something which is affordable and achievable. And even just this week, I've just come back from a conference in Geneva, where I was talking to the whole financial sector around building bridges between the financial markets and infrastructure, and the importance of us looking at blended financing for exactly these types of systems. Because if we're going to be able to meet that financial gap that I presented at the beginning in terms of the billions of dollars, we've got to not only be focused on the right climate resilient infrastructure, we've also got to be focused on the right resilient financial model, which is going to work with this level of OPEX. So those types of OPEX schemes, of course, can come in different forms. And we traditionally have looked at the areas around management contracts, which are sort of in the middle, squarely in the middle of public-private partnerships. We've also looked at concessional models like the build, operate, and transfer, or the design, build, and operate models. And in many financing agreements, because infrastructure, water supply infrastructure, particularly in Africa, has, when it involves concessional finance, has focused on areas with a higher willingness and capacity to pay for the water. The preferred option has often been to go for those types of contracts. But what we found is that when you start to reach out to many of the areas of Africa where the coverage is lower, particularly where you have these small towns, these secondary cities, where the capacity and willingness to pay may be slightly lower, we also need to be innovative in what type of contracting method we can put in place. Many of these small towns, as we mentioned at the beginning, are with a population of less than 300,000. They may have a very small utility that is operating a small network of water in that town, but the capacity of that utility to then suddenly expand it and manage one of these large schemes that I'm referring to is a challenge. And so what we developed over the years, and we published in 2019 using, again, analysis using fuzzy logic, was a method called the Build, Capacity, Build and Transfer, the BCBT methodology, and it's written there at the bottom of the slide. And what this is it's a new type of contracting methodology for infrastructure. It adopts the BOT, the Build, Operate, Transfer, and so the build component is unaltered. The transfer component and the operating component of the BOT are then modified, and you can see that in here. So what we tried to do was introduce during the operations a capacity building component where the contractor who builds the CapEx, so the civil contractor, remains on site for a period of the defects liability, usually for 2 years, to be able to provide the capacity building to the local utility so that they can operate it after that 2-year period. So of course, there's a set of standard benchmarks which are there that they have to achieve, unaccounted for water, the levels of water quality, the pricing for pro-poor communities. All of those components are there, but the utility that was previously on a BOT would never have been able to achieve. We've seen a number of water systems across Africa which have been on a BOT contract, and 2 years after the contractor withdraws from a different type of bank finance, we will see all of a sudden the assets falling apart. There will be leakage, there will be illegal connections, there will be a number of factors which will lead it to be impossible for the local utility to manage sustainably for the future. So with this solution, with the Build, Capacity, Build, Transfer, we are able to introduce a professional service delivery model into these slightly more complex areas and enable them to cover during that defects liability period a way to ensure the sustainability of the asset up until the end of the contract period. And we found this to be, and you can see it in this paper, it's quite an interesting analysis. We found this to be a very good model, and we're currently working with a number of different actors across Africa to expand this in a way that we would be able to then have a more climate resilient way of looking at the infrastructure in those particular areas. So this paper is available in the Water Journal from 2019. So I guess in summary, I mean, it's a really huge pleasure to be involved as an honorary professor with Bartlett. And Bartlett, of course, is really the leading center for infrastructure, and particularly for the infrastructure life cycle. And what I've tried to do in this this brief presentation is kind of introduce climate resilient components that you can add into each aspect of the civil infrastructure life cycle. So I've talked about planning at the beginning. So how can you prioritize based on all of the complexities of Africa, looking at population, where population live, using an AHP tool, multi-criterion tool to help you make decisions on your planning. I've talked about design and particularly the issues around design when it comes to looking at securing the water source itself, but also looking at what are water supply options, which are there. We talked about the isotope methodology. We also talked about the water transversal schemes, which you can use as a way of planning large-scale infrastructure in areas which previously seemed to be almost impossible to reach. I've talked about procurement. So we talked about the build, operate and transfer. We talked about the build capacity, build transfer, and how we have tried to innovate around procurement. So rather than just taking standard FIDIC procedures and using them where we've seen over many years in Africa challenges of sustainability, we tried to modify the build capacity, build transfer and publish it in as many journals as we could so that the academic community can learn from it, but also we as an industry can improve and learn from the success of those kind of interventions. We talked about construction, and particularly I referred to our journal paper in Nature, where we looked at technology selection, and we learned lessons from the 2015-2016 drought to make sure that whatever assets we are supporting with this climate-induced change in the meteorological cycle, now instead of having 2 rainy seasons in many parts of Africa, we're seeing 4 or 5 rainy seasons, but all of them extremely short. So we will find that we will have a period of rainfall of maybe 100 or 200 millimeters of rain, which will fall within a period of 2 days. And then we will have a period of 2 weeks or 3 weeks of intense sunshine, which of course is leading to high levels of evapotranspiration and the potential also for flooding in those areas. So we need to then look at the lessons learned from where we have selected for construction particular technologies. And I tried to explain that during the reference to our paper in Nature. I've also talked about operation and the importance of exploring different types of service delivery models, from community and voluntary models all the way through to looking at delegated management or private sector models. And then finally, around the maintenance issues, I've tried to link that back to the build capacity, build transfer, so that the maintenance, at least for the first couple of years, the knowledge on what valves are in place, what pipes are in place, what type of specifications does the utility need to know about, can be also looked at. And I, at the beginning, was also referring to some very interesting work that we're currently doing using biosensors, where again, we are placing biosensors inside the boreholes themselves, but also in the water transmission systems, to be able to remotely monitor on a dashboard from remote locations in war zones or remote locations which are in areas affected by frequent droughts or floods. We're able to see what maintenance requirements will be there from a dashboard, and then understand from that what type of additional support might be needed, or supply or components might be needed for those areas. So I think with that, I shall stop, and I'll hand back to you, Priti, in case there's some Q&As, and many, many thanks for all the attention. Thank you.
Thank you so much. I think I was kind of blown away by how you started with the big picture and the big challenges facing us, and then moving into very practical tools that we can use to address those big challenges, to deliver infrastructure, but with the rigor that we need. Because my big gripe with international development is that sometimes we see a lot of haphazard kind of approaches, projects, a lot of failures. And I think using some of the tools that you've discussed today throughout the life cycle of the project is vital, I think, for successful delivery of infrastructure for well-being. I could speak more. I have lots of questions, but I note that there are quite a lot of questions for you. We'll work our way through as many as we can in the next 10 minutes. Some of them I think you may have responded to, but you might want to add to. So there's a question from Alejandra about kind of technologies, and I think you did touch on technology selection, but it's about trying to find water in a dry area in north of Tanzania, have drilled 190 plus meter holes with no success. What are the alternatives that you can suggest which are cost efficient?
Great. Shall I, Priti, do you want me to take one or two maybe together, and then I can come back in? Is that okay?
Take this one, and then I can group them as we go along.
Super. Okay. So for Alessandro, Alessandro, I'm aware of the areas that you're referring to in Tanzania, and I think the challenges we faced, and I'm sure you'd agree with me, Alessandro, over the years, is that we feel that 190 meters is quite deep, because we were trained very much to understand that our threshold for drilling was around 100 meters. I think the reality is now, again, with this changing meteorological cycles, there is a need to invest heavily in the types of technologies that I referred to for groundwater investigation. And this will help you identify the saturated zones, the areas where you may have high levels of salinity as well, but also those which are perched aquifers, which I'm sure when your drillers are looking at 190 meters, they probably do come across these perched aquifers. Water starts to come out of the well, and then they believe that they've actually got a water system. But of course, once they start doing the step drawdown analysis tests, immediately they find that there's not enough water in the hole. So I would encourage you and others who are on the call to read through some of the academic literature that I referred to in this presentation, and do feel free to contact me if you want any more technical support in those types of drilling operations. Thank you.
Thank you. The next question is from Aidan. How much the numbers of people, employment in decent work could be obtained by investment in necessary water infrastructure, and how would that impact the migration crisis from sub-Saharan Africa to the Med?
Wow, that's a very big question. I mean, I think a lot of the investments that are happening now in water supply are happening along the migration routes. And again, we are very involved. I'm very involved in large infrastructure projects, which has at its core the objective of increasing social cohesion between people who've been displaced or who are migrating and the host communities themselves. And so the importance of developing these water systems is obviously not only to improve the health, well-being and economics of the users in those areas, but it's also to provide some level of stability to try to prevent as much as possible, both internal migration within countries, which is a big challenge, but also outward migration. So people moving from certain parts of Africa to other parts of Africa, whether that's south towards South Africa or north towards Europe. Yeah, that's what I would say. I think there's a huge question, that particular question.
No, absolutely. The next question is from John Kelsey, who's a very dear colleague of us in the Bartlett School of Sustainable Construction. And if I may say so, has substantial experience of working overseas in a range of settings on complex projects. And I mean, he rightly highlights that the huge bugbear in infrastructure is maintenance. Is there a process for measuring actual depreciation of existing infrastructure against targets?
Yeah, absolutely, John. This is the key issue. I mean, I would unpack it, John, in this way, that I think historically what we've done is we've often separated the capex from the opex. And given that the private sector is growing and is increasing in Africa, it's definitely becoming more sophisticated, whether that's in the water, the energy, the roads, etc. I think we need to look at packaging and clustering contracts to make them large enough so that we can look at some sort of economy of scale. Now, this will improve, of course, the level of competency of the contractor, the financial viability of the contractor, but it will also promote joint ventures, which can bring up more private sector, local private sector in these areas. Now, once the local private sector in these areas is more familiar with the asset that's been built, there's much more likelihood, at least from my experience, John, of them undertaking maintenance, because they'll understand what's built. If we look, for example, the 1990s, the early 2000s, there was a lot of assets built across Eastern Southern Africa, at least, by the Chinese. And a lot of those were built not necessarily with local private sector. And so you found that it's difficult for that local private sector to undertake the maintenance of those particular schemes. I'm not saying that that was the only reason, but it's definitely one of those reasons. But it's an area of research and thinking we need to continually look at. But I do think one of the learnings from my work is that clustering the contracts is very important. And I think the build capacity, build transfer modality, it's not the silver bullet, but it is an important step in the right direction to bring CapEx together with OpEx.
There are a few questions around, once again, wells. I think I'm going to pick one of those, which is from Binu Arikwal WaterAid. And I think this is in relation to kind of groundwater kind of conditions in India, which I relate to, that the problem with unregulated usage of groundwater is that you have groundwater tables dropping rapidly, and that results also in contamination of water due to geological factors. So I just wanted a brief take on that.
Yeah, I mean, absolutely. I think the Punjab is the well-known example, isn't it, over the years of this. And certainly I was working for a number of years in Madhya Pradesh, in Bhopal, and was very familiar also with the complexity of the hydrogeology of central India, where not only does the overexploitation of the groundwater lead to reduced yield, but also leads to leaching of fluoride, and in some cases even arsenic, into the groundwater, which is even more of a challenge because of the fact that we're then, literally poisoning our water supply systems. So I think we need to look at, innovative ways that we can then, monitor the drawdown on the groundwater. I mentioned our work on biosensors, and I'll certainly, be collaborating closely with Professor Priti and others there on pulling together that evidence and trying to bring that also to the academic audience. Because I think biosensors have got a really key role to play in relaying real-time information on groundwater, which will send alarms to enable us to understand what's been the impact of these different withdrawals on those particular schemes. But that alone, of course, as you know, and colleagues in water aid are very familiar with, is not enough. We clearly have got to look at the whole enabling environment. We've got to look at the regulatory environment. We've got to look at all of the institutional structures which are there in that particular area of India or any other part of the world. But happy to contribute at least on some innovative ways that we could try and look at this from a biosensors perspective.
Thank you. I'm going to squeeze in fairly quickly 2 or 3 questions. One was around, did you face any challenges on kind of the contract, the BCBT contract approach in terms of operation and maintenance? Are you doing kind of similar, are you doing research in Nigeria? Because that's of interest to Engineer Joy. And also indications on water quality. So how would you look at water quality when you look at recharge potentials of aquifers? And I think that's as far as I think we can go.
Super. Yeah. In terms of the question from Joy, I'm not doing any specific research in Nigeria, but I'd welcome the idea of being involved in Nigeria. In terms of the BCBCT, I mean, the biggest challenge is it's really the fact that we're trying to solve a governance solution. So in many of these areas, of course, the employees of the local government are working in a utility, and many of them may not even come from an engineering or a water background. And they are full-time employees of the government. And what we're trying to do is create more capacity of those local utilities using this BCBCT. We can't displace, of course, local civil servants, but at the same time, we need to reform the way that they're doing things. That's a big challenge, and that we've seen in a number of countries as we've expanded this, into other areas of Africa. And then maybe finally, on the water quality, there are many factors on the water quality, ranging from the microbiological quality to the chemical and the physiochemical side. What I'm really interested in on the water quality is looking at surrogate indicators, because the concept that you can set up a water quality laboratory for every one of these types of schemes is very difficult to finance and to manage. And so looking at surrogate indicators, like, for example, electrical conductivity as a surrogate for salinity, is something which will really help because of the handheld probes or the different types of technology that you can deploy at field level, which will enable you to be able to monitor that water quality in a day-to-day way, in a practical way, in those areas. Yeah, thank you.
Thank you. I'm going to squeeze in kind of a very quick, big picture question. This is the last one, I'm afraid, which is, does your research go beyond frontier and look at inter-country transfer of water?
That's a great question. It does, yes. We are currently running a regional program across Somalia, Sudan, Ethiopia, Uganda, and Kenya, which is looking directly at the use of water resources for the refugee and the host communities in those areas. Of course, the bigger water catchment management writ large can only be assessed using these types of tools that I'm referring to. But it's key and essential component of securing the climate resilient water source for those particular communities. The reality, I think, at this stage is that the borderlands areas, the areas which are between one country and another, are areas where we have a very high population density and a very low level of asset coverage. And so these are areas in which we need to deploy these types of technologies that I've referred to in this talk, to try to improve the health, well-being and livelihoods and economics of those areas, so that we have more prosperity going into the SDGs.
This is fantastic, and I want to thank you for sharing your experiences, but also the fact that you're dealing with real life challenges at scale. I mean, Kit Kagol from UNICEF highlights that in Ethiopia, they're looking at, when they look at drilling, they're looking at depths in the range of 300 meters. I mean, that shows how serious the issue is around water availability, water resources and scarcity. And with climate change, I mean, this problem is going to kind of expand and affect communities. So I'm really grateful for you for spending time with us, sharing those experiences. I'm sorry we could not respond to all questions, but feel free to email us and we can send you responses. And the session has been recorded, so feel free to share with your colleagues, with your friends who may be interested in this. But thank you so much for joining us today. Thank you.
Thank you.